Thank you again for joining us today for this new webinar series with ALSET. Today we have the pleasure to have two very interesting presenters on the very fascinating topic about how they generated some synthetic data on student activities without breaching, of course, confidentiality. So we have Prof. Tay, who is a famous professor at NUS, working with the Department of Mathematics and the Department of Computer Science, and also the Tembusu College at NUS. Prof. Tay has a very thorough experience in many other prestigious universities at Princeton, MIT, and a PhD from Harvard. His main research interest is in performance modeling and in database systems. He has supervised the work of FENG Ben, who is currently pursuing a bachelor's degree with the School of Software Engineering at Sichuan University. And FENG Ben was an exchange student at NUS during the last semester. So I will give the floor right away to Prof. Tay to introduce their research. Thank you very much.
Hi, first of all, let me thank ALSET and Kevin for suggesting that we give this talk and providing the data for this talk, and to thank Alex for setting this up. So FENG Ben is going to do the technical presentation, but let me provide some context for what he's going to present. So what FENG Ben is going to talk about is part of a larger project of mine about synthetic generation of data. So nowadays there is plenty of data around. Why do you need to generate synthetic data? So there are three scenarios why I think you want to have synthetic data. So let me describe the general scenario, then I will shift the focus to student data. So in the general case, you may have an empirical data set, but for some reason, you might want to have a larger version of that data set. So this is what I call the scale-up problem. So for example, you may be a startup with a particular data set for your application, and you have the happy problem that you are growing rapidly, and you want to know, let's say 6 months from now, what your data set will look like 6 months from now, so that you can prepare for it. You can size up your system, your software support, etc. So since you're trying to project into the future, you have no choice but to generate fake data that will imitate what it's going to be like 6 months from now. So this is the scale-up problem where synthetic data generation is necessary. And then there's a scale-down problem. You may have a humongous data set, something like Facebook, for example, where they have their data can be viewed as a graph with billions of nodes and trillions of edges. Now, if you are developing an application for such a big data set and you want to test your application, debug your application, you really don't want to be running your application on the real data set. You want a smaller version of the real data set. But you want that smaller version to be similar to the large data set. So you want to scale down the data set. Now, since you have this large data set, the obvious idea would be to randomly sample from the large data set. So maybe you randomly sample the nodes and you randomly sample the edges. But that idea doesn't work very well, because if you take a graph, a connected graph, and then you randomly sample, you're going to end up with a disconnected graph. So you will not have a social network in that sense. So the scaled down version, although you have some empirical data set, the scaled down version is non-trivial also, because you have to preserve the structure of the large data set. And then there's so there was a scale up problem, the scale down problem, but there's also a situation where you might want to have a synthetic data set that is the same size as your empirical data set. Now, it might seem strange that since you have empirical data set, why would you want to have a synthetic version that is the same size? So let's think about, let's say maybe you're a hospital, okay? You're a hospital, you have a lot of patient data, but you don't have in-house expertise for developing applications to process this patient data. So you want to outsource the problem to some developers. But patient data is private, so you don't want to give the developers the private data. But the developers need some kind of data to test their applications. So what you want to do is give the developers a synthetic version of your patient data. Now, this synthetic version of the data will hide all the sensitive details. Now, it might seem like, so this is kind of like the anonymization problem. You might think that you can just replace all the names and addresses with random numbers or whatever, but this actually doesn't work very well. There are famous examples of where anonymization failed. So straightforward anonymization doesn't work very well in practice. And our idea is not to anonymize the data for privacy reasons, but to get around the privacy issue, we just synthetically generate the data. Synthetically generate a version that has the same properties as the real data. Okay, so that's the general context, right? And my students have done work on this issue. Now, for ALSET, which concerns student data, you also have these three versions of the problem. So in the scale up example, for example, in the case of scale up, in the last few years, many computer science departments across the world have seen a tremendous increase in enrollment. So let's say you are head of a department, computer science department, and you want to provision the department so that it can handle the growth in number of students. You want to worry about whether you should hire more teaching staff. You worry about whether your hardware can handle the increase in student enrollment. You worry about, in the case of NUS, whether you should have more classrooms, build a new structure to accommodate all these students. So this is a scale-up problem, right? You are going to predict 2 years from now how big the student enrollment is going to be. The scaled down version, okay, so NUS, let's say, has something like 40,000 students, but with social distancing because of COVID, you might want to reduce the population to say just 15,000. So now you have this data set of 40,000 students. You want to know what if there are only 15,000 students on campus? What would be the demands on the bus services, on the canteens, etc. So this is an example where you want to scale down the data set. And then the same size problem, even with 40,000 students, let's say you want to understand how, if Singapore goes to phase 3 and you release all these constraints on movement, how do students move about on campus and where are the vulnerabilities in terms of COVID infections, let's say. So in that case, you want to understand how students move. You might want to develop an application to understand how infection might happen on campus. But student movement involves student identities, very private data about where they go, who they meet, etc. So again, in that particular case, you might want to have synthetic students rather than real students. For the developer, ALSET has all this data about where students are on campus, but ALSET cannot give this data to the developer. So anyone who wants to develop an application to understand how infection can happen on campus in the dormitories, for example, the developer cannot have the real data. The developer may have to do with some synthetic version of the data. And I'm hoping that I can help ALSET come up with the techniques to generate synthetic versions of the data that they can release to the developers. Okay, so this is what this part of this is what Feng Peng is doing. Feng Peng was here as an exchange student last semester, and he did this project that focuses on Wi-Fi connections. Now, there's a lot of information you can get from Wi-Fi connections, how long the student is connected, the movement of the student, etc. You can deduce from the Wi-Fi data. Okay, so now I've provided you with the background, and let me hand this over to Feng Peng, who will now describe what he has done.
Thank you, Professor Tay. Good afternoon, everyone. I'm Feng Ben. The project I'll present today is HMM-based synthesis model for Wi-Fi connection data. Developers can do a lot of things with student data collected by school, but for privacy reasons, student data should not be freely available. One alternative way is to generate synthetic data that is similar with the real data and only give the developers the synthetic data. So our work focuses on Wi-Fi connection trajectory and try to generate synthetic one which can be freely available. The Wi-Fi connection data we use is collected from all the size points on NUS campus, and record has 16 attributes. 8 are used in our project, which contains student and MAC token, the time that the connection starts and ends, and where the connection happens. Due to overload of access point or movement in the building, devices may generate multiple connection records in the same location. Our work focuses on device movement between locations instead of movement within the building. Therefore, we merge fragmented connection records. After pre-processing, we can get the information that a device connects Wi-Fi at a location, L. L contains the device token, where and when the connection happened, as well as stay and connection duration that the device at that location. And this is an example of pre-processing. In this table, it shows 2 records that device 001 connect at S17. The first row is on the 2nd floor of S17, and the second row is on the 3rd floor of S17. Because the session start time on the 3rd floor is only 1 minute later than the session end time on the 2nd floor. Therefore, it would be merged after the pre-processing. In our project, we set the threshold of this 2 time to 10 minutes. After merging, the session start time of the connection is 10 o'clock and the session end time is 10:20. And the location is S17. The duration that the device spent at S17 for 20 minutes, but they only use the Wi-Fi for 19 minutes. So this table is the duration. Before modeling, we first do some data analysis. This is the number of records per day for 2 weeks data. And this is the number of students and devices using Wi-Fi per day. We can see the number on work days is much more than on weekends. We think the reason should be that there are many students live off campus or spend weekends out of school. They will not use Wi-Fi on campus during that time. Next, we analyze the number of connections over time. This row is the Monday, Tuesday, and Saturday for the first week, and this row is for the week 2. There is a large difference between the work days of the first week and second week. But for the second week itself, they are similar. For the weekends, the distribution looks very similar. We think the reason should be that this week is the first week of the semester. A large part of the course are not started, so the distribution of online number varies quickly. In the second week, as the courses start, students' activity begin to be regularly, so the number of online people on each workday on the second week shows a more similar distribution. The weekends are basically not affected by the courses, so it shows a similar distribution, which indicates students have regular activities on the weekends. Next, we analyze the distribution of total connection time of device, which means how long a device uses Wi-Fi for a whole day. On work days, the total duration shows a bimodal distribution. It peaks around 10 minutes and 1 hour respectively. For weekends, the distribution peaked around 10 minutes and then dropped. The reason for this phenomenon may be that there are more devices that need to record notes in the classroom on the working days, such as laptops. This device usually connect for a long time, so the working days have a peak around 1 hour, but the rest of the day does not have. After the analysis, we start modeling. We construct an architecture of data generation model. We have 2 things to do. Firstly, we need to model the empirical data in order to extract the feature. And secondly, given some initial states, we can use our feature model to generate the synthetic data. In order to model the empirical data, we regard the movement process of device between locations as a one-order Markov process, which means the next location of the trajectory is only depend on the previous one. Then we can use a hidden Markov model to express this progress. Hidden Markov model has 5 elements, and ICE is the hidden state. In our project, we regard each location on the campus as a hidden state. O is the observation value set. We regard the duration information of the device as observation value. A is the transition matrix, which indicate the probability of transition from Si to Sj. And the B is confusion matrix, which denotes the probability that the observation value is Oj when the hidden state is Si. And pi is an initial state probability matrix. The Markov model can well describe the process of the device transfer between different locations in a period of time. But the time span of Wi-Fi connection data is 24 hours. And the probability of state transition will change with time. For example, In the morning, the probability of transferring from campus subway station to the Bs will be significantly higher than at midnight. In order to solve this problem, we construct a temporal Markov model. We divide one day from 0 o'clock to 24 o'clock into 24 time slots and construct hidden Markov model for each time slot. Besides, we have a transition time site, which means the time a device needs to move from one location to another. We assume the transition time doesn't change with time. After constructing the model, we need to calculate the parameter. A trajectory of device consists of the connection information at several locations. This is an example of L, which is obtained after pre-processing. We first format the trajectories into transition tuple format. A transtuple has 3 elements: the information at start point, the information at end point, and the transition time between these 2 locations. Then we define the expression of a transtuple under some condition like this. And this expression is the tuples which session start time of start point is in time slot TS. And this is the tuples which session end time of the start point is in time slot TS. The hidden state is very simple. It is about 200 locations on campus. And for the observation state set, it is all of the duration attributes of start point in the tuple start. And in our project, each hidden state of the data has its corresponding observation state. So the maximum likelihood estimation of the hidden state transition matrix and the confusion matrix can be calculated according to the frequency. For the transition time between 2 locations, we can use the distribution from the empirical data to express them. After constructing the model, we can begin to generate the synthetic data. The following steps are used to generate a trajectory for one device. If we want to generate 1,000 trajectories, we can repeat it 1,000 times. Init state is required before generation. It includes 3 attributes: start time and start address indicate where and when a device starts to connect the Wi-Fi. And since THMM cannot determine when the generation process ends, so we need a length in the initial state to indicate the number of locations that the device appears in a day. We use empty list to store the final result. And in the first step of our generation, we get the start time. We get the start time slot according to the session start time. Then we will know the duration according to the observation value and confusion matrix. After knowing this, the information in the location L1 can be constructed. Next, make the length of the initial state -1. If the length equals to 0, we will get the final result. Otherwise, we can use L1 to get next location with transition time distribution and update the init state in the next location. Then repeat the whole progress until the length equals to 0. And then we can get one trajectory for a device. In the project, we extract init states from the empirical data and use them to generate the synthetic data. Since our target is to generate synthetic data which has similar feature with the empirical one, we use 3 metrics to evaluate our model according to 3 elements in the Wi-Fi connection process: device, location, and time. The matrix contains total connection time of devices, number of connections in different locations, and the number of connections over time. For the total connection time for devices, the right one is the distribution of empirical data. The green one is the synthetic data. We can see that these two are very similar through the cumulative distribution function. These two distributions are regarded same according to our test result, and all of the 14 days are the same. For the number of connections in different locations, the conclusion is the same with the total connection time distribution. No matter weekdays or weekends, the synthetic data has similar distribution with empirical one. Next, the number of connections over time. Synthetic data has an obvious difference from the empirical data, especially for the weekends. The reason for this should be that we didn't constrain the number of connections over time in the model. Trajectory generation is implemented by transition from one state to another in THMM, and the connection time of the previous state will affect the connection time of the next state, which will finally affect the number of connections over time. If the number of connections per device is large, the deviation introduced in the generation process will be accumulated and the result will be a little bit different. And we do 2 extra work in the final of our project. The first thing, we try to use the state duration distribution at locations and the steady state in hidden Markov model to generate the entire distribution of state duration. Our goal is to explore a method to obtain entire state duration distribution based on HMM and the distribution at locations instead of using synthetic trajectories to get the distribution. For the steady state probability, we can calculate using the transition matrix of hidden Markov model. And for the distribution for state duration at locations, we use a 2-term exponential function to express it. After that, we calculate the entire distribution according to this formula. Fi is the state duration distribution at a single location, I. This is the entire state duration distribution for the whole campus. And we can see the blue one is the distribution which is obtained by the synthetic trajectories, and the orange one is our synthetic distribution. We can see their trends are similar, but orange one doesn't have the little peak in the right circle. The cumulative distribution function also show this problem. And the main reason should be there is a little peak in the empirical distribution of a location, but our 2-term exponential function don't express it properly. So in the future, we can find a more proper function to express this distribution, and we think we can get a more accurate final result after we improve this thing. Next, the second thing, we get module enrollment data and program enrollment data recently. It has this information for students, such as their academic career. And we use this to divide the students into two categories, undergraduate student and graduate student. We find the transition matrix is different between undergraduate student and graduate student. This is the heat map of the transition matrix. We circle some different places in the figure. And after dividing students into several categories, the synthetic data would be more accurate after using this to generate the synthetic data. So in our project, we show some characteristic of Wi-Fi connection data and analyze the reason. Then pre-process the data and construct a model, THMM, to extract the feature from the empirical data and generate synthetic data using initial state. Then we use 3 evaluation methods, which shows our model can generate synthetic data, which has similar feature with the empirical data. In the future, we can improve our project through these ways. Now we can see the constraints between devices. For example, the trajectory of 2 devices should be similar if they are owned by a student. However, our algorithm may generate 2 different trajectories for these 2 devices. And the second thing is we can modify our model to make the number of connections over time more similar with the empirical data. And that's my presentation. Thank you for listening.
Well, thank you very much. That's indeed a very fascinating topic, and your methods seem very efficient for a lot of many opportunities. I suggest that we open the floor to questions through the chat panel, or if you want to just unmute yourself and ask your question directly.
Hi, thank you for the presentations. I have a question, maybe a dumb question, so don't laugh when I ask this. I see that you have tried to reproduce certain characteristics of the data, right? The statistical distributions and some measures of that. But are there? Does your synthetic data preserve the information content? For example, if I were to make some conclusions from the original data, and let's say I work on the synthetic data, am I likely to get similar conclusions about the research questions I might have? Or will it be completely different? Or it will be, so I'm just trying to see, yes, we preserve certain things, but what will we lose in this process? What are we likely to lose? And is it going to be very detrimental?
Okay, so this fundamental question is an excellent question, fundamental to the entire approach. Now, when you want your synthetic data to be similar to the original empirical data, you have to define what it means to be similar. So there are any number of dimensions to this similarity. So in this, what FENG Ben is doing is looking at the number of devices, number of connections, connection time, etc. But there could be other aspects that is not captured by these 3 metrics. So in general, if you just include more aspects of the student, let's say what module he's taking, whether he's a graduate student or undergraduate student, whether he is with the engineering faculty or the science faculty. The more dimensions you add into the problem, and if you can capture more of these dimensions, then of course your data is going to look more similar to the empirical data. So speaking generally, there's a feature set. The more features you put into this feature set, the more similar your synthetic data is going to be when compared to the empirical data. And you have a higher confidence that what you want to capture would be within the feature set. But it's a double-edged sword in the sense that the bigger the feature set, the harder it is for you to generate synthetic data that is going to satisfy all these features. So, you know, things become NP complete very quickly. So when the user, so some developer comes to you and say, give me some synthetic data that is similar to the empirical data, we rely on the developer to tell us what are the features that you want. And then we make sure that we capture those features and reproduce those features in the empirical data, in the synthetic data. I think it would be intractable to try to capture all features. Yeah.
Yes.
Now, somewhere in the audience is my former PhD student who is now working for some big travel company. And his PhD thesis was on replicating how you can come up with a framework to replicate user-specified features. So what you have is a set of tools, and then maybe the set of tools has A, B, C, D, E, and then you pick and choose. You say, I need B and I need D. Okay, then you apply these two tools and get empirical, get a synthetic data that has features B and D. For somebody else, he may say, oh, I don't need D, I want the A, B, and C. So then you just say A, B, and C, and then you apply those three tools, and then you will get a synthetic data that has properties A, B, and C. So I don't think we can get a synthetic generator that would have all the features that you want and be able to capture everything faithfully. It is futile to aim for that, and is computationally impossible, intractable. So it's more feasible to have a tool set, and maybe ALSET should aim to have this kind of a tool set and say, okay, what do you want? You want A, B, and C, or you want B, C, and D? Yeah.
Got it. Yeah. Thank you so much. Yeah.
Sure.
There were two questions on the chat, so maybe.
Yeah, I'm looking at it. So, does the HMM capture express information like a student is likely to use a phone device for 15 minutes at canteen during lunch? Or Feng, can you answer that?
Like a student is likely to use for the work we done right now, it don't have this. It doesn't capture this this feature. We can only capture the transition feature of the devices, and we don't divide the device into several categories. So this is.
So there are three key features in this particular question. One is phone device or laptop. One is the location, canteen, and the other one is lunchtime, right? So the lunchtime and the location, that is already in the what Feng Peng has captured. What Feng Peng has not captured is doesn't distinguish rather between a phone device or laptop. So as he mentioned towards the end of his presentation, a student may have two devices, let's say a phone and a laptop, and in his analysis, he has not distinguished between the two. If there's a way to tell which one is a phone and which one is a laptop, then yes, we can separate the two of them, and then we can actually answer the question. I think the FENG Ben confirmed for this, right? The HMM itself will be able to, you can have a hidden state. Do you need a hidden state for phone and device, or should you just tag the device as phone or laptop? If you want to model phone versus laptop, how would you do it?
I think if we want to get these things, we should first, firstly, we should divide the device into several categories, and then capture their features from the empirical data. I cannot come up with a method to directly capture this feature through our model now.
I think what might be necessary is to analyze for a particular device, to analyze the movement of the device, the connection time of the device, and then and then classify it as either a phone or a laptop, right? If the MAC token cannot tell you whether it's a phone or laptop, then you have to look at the behavior of that MAC token and then classify it accordingly. And once you classify it, I think you can build the HMM for it.
Yes. And for Taha's problem, in the practice of our project, if there isn't a transition probability from the state to the final state, we just remove these tuples from the final results. We regard it as an unuseful initial state, and we remove the synthetic data. And this the number of these illegal tuples are not very large, so it will not affect the final result of our project. Okay.
So Jiang Wei is answering Taha's question, and Taha's question is whether how Taha is suggesting an alternative way to model the number of locations that a device visits. So the way FENG Ben models it is to, at the get-go, before you start the trajectory, you specify this trajectory visits how many locations. And now if it visits 15 locations, then you generate 15 stops in this trajectory. And Taha says that maybe you don't do that, but within the HMM, you have a probability for when you reach the final state. Yes, you can do that, but being a probability, that also means that you have a probability of generating a trajectory that has 200 locations, let's say, and then you end up getting trajectories that are not very meaningful, right? So I think it is a possible alternative, and it's not clear that FENG Ben's model is superior to the alternative one, but FENG Ben's model of specifying the trajectory length at the outset avoids some artifacts that you might get if you don't do it that way. So FENG Ben, the next question.
Would model using a mixed HMM help to improve the model of the double exponential currently modeled? the double exponential is a little bit simple to model the data. So if we use a more complex model, we think the results should be more accurate than what we have done now.
I think the idea that FENG Ben was trying to check out regarding the double exponential. So so in the main body of work, FENG Ben was generating the synthetic data by generating synthetic devices. So he has, if you have 4,000 devices on campus, you generate 4,000 fake trajectories, one trajectory at a time. Now, that is certainly one way to figure out, say, what is the connection time distribution of the students aggregated over the entire campus. But if you are not interested in specific trajectories, you're not interested in connection times of specific students, then what you can do is, rather than generate 4,000 trajectories, you just look at the steady state distribution for the probability that a device is at location X or at location Y. So that was what he was trying to do. And for that, he needed a probability distribution for the connection time distribution. Once you have the steady state Markov chain probabilities and the stay duration distribution, you can generate the campus-wide stay duration distribution, not just the location-specific stay duration, but the campus-wide stay duration. So for that, you need the stay duration distribution. Now, whether the stay duration distribution is a double exponential or not, that is not the key issue. What he was demonstrating is you need the stay duration distribution to be good enough to have enough feature to capture this slight bump. If your synthetic distribution for the stay duration can capture that bump, then you'll be fine. But if your stay duration cannot capture that slight bump, then you are going to get some inaccuracies. So that was just a proof of concept that using just a steady state probability and the stay duration distribution, you can generate a campus-wide the synthetic general campus-wide stay duration distribution. Next question from Lars. You say 40s, developing synthetic data sets for data sets having 40 subjects and 300 features per subject. What would be a subject?
I meant students. Let's
40
say 30 students. So I'm looking at fat data sets as opposed to longer matrices.
Okay.
More features, but less number of students, for example.
Okay, so let's say you are thinking about 40 students with 300 properties that you're interested in.
Yes, yeah.
I think that this particular approach wouldn't work very well. It's kind of like the central limit theorem, right? You need at least 30 for things to work out. So for 40 subjects, they are going to have idiosyncrasies, especially with 300 features. So it's going to be very sparse in terms of data points. And then with a very sparse features, it's going to be very difficult to come up with the relevant distributions to capture the correlations. Now, in order to know the correlation between one feature and the next feature, you need to have enough data for you to capture that correlation. So if just 40 subjects, you won't have enough data to do that, I think.
Thank you.
Sure.
I had another question also, but there are other questions, so you can answer the other questions and then come back to my question if you have time.
Okay, so let me look at the next one. Okay, it's whether the generating synthetic data retains privacy better than anonymization. Okay, so anonymization, if it's successful, is perfect, right? But it's very hard for anonymization to be perfect because of side channel attacks. If you restrict your attacker to just the data set itself, the anonymized data set, then anonymization would hide all the privacy issues. But what happens in practice is always there's some side channel, some other data that the attacker has access to, and by combining that other data with the target data set, he can de-anonymize. So if you just go online and check, there are many examples where you have an anonymized data set, and then the attacker uses some other data set to de-anonymize the anonymization. So the anonymization doesn't work very well in practice if the attacker has access to other data. In the case of synthetic data generation, because the data is completely synthetic, there's no privacy issue involved, except that the synthetic data is supposed to be similar to the empirical data. So when you say the synthetic data is similar to the empirical data, similar in what sense? Now, if it's similar in terms of density function, let's say, then when you look at the synthetic data and you look at the density distribution of the synthetic data, then of course, now you have an idea of what the density distribution looks like for the real data. So in that sense, the synthetic data is exposing the correlation structure, the density distributions, etc. And you can't avoid that because that is the very meaning of similarity. If the synthetic data is going to be similar to the original data, then of course, by analyzing the synthetic data, you will get to know what the distribution is for the original data. So that information you cannot hide. But the information about specific students, etc., you don't have that because the data is completely synthetic. Yeah. So Kevin has a question, building off last question about sample size versus number of features. Is there a rule of thumb about the size of a subgroup of interest and number of features that we would be looking at staying above in order to adequately model it? So it is the sample size versus the feature set. So I'm going to pass this to Jiang Wei instead. Jiang Wei, you want to answer that question? Jiang Wei was my PhD student who worked on synthetic data generation in a more general setting. He's somewhere in the audience, but I don't know whether he's...
Yeah.
Okay, can you answer that question?
Yeah. Thanks. So back to this, basically the trade-off between the sample size and the number of features. I think that the complexity is not really about how big you want to have the sample data is. It's always the complexity in the sense that how do you generate such a huge volume of like features. Of course, in the sense that sample size will go kind of will grow. Oh, sorry, complexity will grow as the sample size grow, but the complexity doesn't really come from like sample size, in the sense that the complexity limited. Sorry, the limitation of generation, data generation is not really limited by the sample size. It's limited by the features that you want to preserve. And talking about the features, that another concern is that how overlapping these features are. Is the more overlapping, then the more constraints that for those features that they will have to interact with each other. And at some of the time that they have to probably like contradicting to each other, where this will comes with a cost where you want to have certain trade-offs among the features that you want to preserve. And then, but if the features are basically isolated in the sense that they are mutually exclusive, then basically the complexity is just there. Individually, how complex that you want to generate the feature is, then you will just grow linearly with the number of features you have. Yeah, that's basically the answer. But there's no basically a good rule of thumb about the size of the features. You can have probably hundreds of features, but if they are not that overlapping, then I mean the generation complexity is pretty like low. But if you might have just 2 or 3 features that you want to preserve, but they're highly overlapping, which probably will kill your basically generation. And the sample size is just basically a dimension that how many you want to generate. But from the algo point of view, sample size is not always a concern.
Thanks, Jiang Wei. So let me back up to Lark's second question. He says 3D data sets, n students, n features on each student over a time period of L days. So I think what FENG Ben has done is already maybe can be characterized as 3D data set, because you have n students and 24 hours, and he's modeling each hour differently, so that you can extend that to L days. The only thing that so this thing about n features on each student, so for example, the feature might be whether you're undergraduate or you're a graduate, whether engineering student or science student, whether features like this. I think as he shown you, the heat map, the transition matrix for whether an undergraduate or graduate looks different, but it's just a transition matrix, right? So you can use, once you know the fraction of students who are undergraduates and you know the fraction of students that are graduates, then you can use these 2 transition matrices to generate their trajectories and then combine their trajectories according to the proportion. So I think it's not going to be a problem if you are thinking about features in that sense.
Okay, my question was more, to see if temporal correlations will also be handled. So I'm thinking of at least 3 correlations, at least. One is the correlation between features. The second thing is there could be a temporal correlation. And if you're looking at locations, there could also be a spatial correlation. So at least I'm thinking of that 3 dimensions. So I was just trying to see if, I think you answered it in the sense, whatever you want to be preserved can be preserved, right? So that I understand as the general answer. So is there anything more you would like to comment on? That was my question, the basis for my question. Thank you.
I think, and FENG Ben can confirm this, I think, so what he has done is looking at 24 hours a day and say that the transition matrix is different for 24 hours a day. So in that sense, take care of the temporal feature, right? So if there's some other feature that would affect, say, the transition matrix, I think you can just refine your transition matrix further. That's certainly one way to do it. So I guess that there's more than one way of attacking the problem. You can either modify your transition matrix, or you can modify your hidden state. And I'm not enough of an expert on hidden Markov chain to know what is the better option. But as Jiang Wei says, it just get more complicated, and it can kill you if you try to capture all the features.
Thank you very much.
Sure.
There's one other question that has come up, Prof.
Yeah, okay. The synthetic data appears to be dependent on the data generation mechanism. In this case, was used. Are there other models that can be used to generate synthetic data, which will still be similar to the empirical data? Also, in say other application, what if the actual data generation mechanism is not known? For example, generating of psychology data of students. So the hidden Markov chain model for generating the data was the obvious idea, because the data that we got from ALSET was Wi-Fi data with students moving around. So this is we needed a mobility model. So the obvious idea for modeling mobility of students was hidden Markov chain. Now, if you are considering, let's say, modeling the psychology of students, then that is something that I'm unfamiliar with. I have some experience with mobility models. I have zero experience with psychological models. So I will need to know what kind of psychological modeling is considered accurate and useful and tractable, and then see how that can be factored into the data generation. Now, the technique, the framework that Feng Peng has demonstrated, I think is not specific to hidden Markov chains. You could be some other models. So I think we are open to that.
Yeah, Prof. Dave, let me add on to this. Yeah, I think that for this psychological data of students, another thing, basically another kind of generative model, it could be the recent like buzzword for the so-called GAN, generative anniversary network. So that kind of generative methods will allow you to generate certain kind of data. For example, basically, same here that I'm not familiar with psychological data of students, but let's talk about psychological like patients. Let's, for example, we want to generate certain data where the patients has certain psychological disease 1, disease 2, disease 3, disease 4. Now, let's say we want to generate fake data of students or patients that having psychological disease 1. Now, in that case, as long as we can extract the features or vectors like in certain way, in a proper way, the generative adversary network might be able to give us a certain data set which has the distributions or has the where the values falls in that category where, for example, the students have certain like psychological disease falls in that pattern. So that kind of generative model is another alternative. But the problem here is that this kind of generative methods is more related to generate a certain cluster, in the sense that you are trying to generate a data that has for example, certain disease or falls in certain category and all those. So, but that's a limitation of the data. But if, for example, if you don't have any labeling of the data in the sense that you don't know, how do you want to classify the students? How do you want to put similarity among the students? Then generative GAN, generative adversary network probably is not operation here. It's not an option here. Then we have to go back to the classical generative like methods, basically using typical like statistics, using features to kind of realize those kind of statistics. Yeah, I mean, this is something that on top of my mind that to complement that what Prof just mentioned.
Well, thank you very much. I don't think we have more questions from now on, and I don't want to take too much of your time neither. Thank you again for this very good technical insights and the fruitful discussion afterwards. Please join me all for to give a round of electronic applause to to Prof Tay and FENG Ben. Thank you very much once again. And we will post the recording of the event on the YouTube ALSET channel in a few days. Thank you again. Thanks.
Thank you. Bye.
Thanks very
Thanks,
much.
Feng
Thanks,
Feng.
Alex. Thank you.